Hello, I'm Benjamin Miss. This is Physiological Psychology, Hypothalamus, and Homeostasis. For this segment, the key things to keep track of are these. What is homeostasis? What nuclei of the hypothalamus are involved in regulation? And describe how mechanisms of hunger and thirst can influence body weight. Well, the first thing to think about is this. What is homeostasis? Start by measuring your heart rate. What this generally means is you look at some kind of clock, you take your pulse, and you measure for about 10 seconds, and then multiply that number by 6. And what we're looking at here is, how are we doing? How do we use heart rate? How do we understand homeostasis? And what can things tell us about our engagement? Well, it's interesting. You've probably heard about how students just aren't the same way they used to be. They were so much better. And, well, I don't think that's true. This is a 14th century painting, right? So we're talking the 1300s, and it shows us a class. And, gosh, those kids today, are they just doing a terrible job? How many of them are paying attention? How many of them are, I don't know, sleeping, flirting, doing something else? The idea is we have this expectation about how things are that may not necessarily match the reality of how things actually are. And when it comes to attention, how do we measure it? How does your body regulate your ability to attend in a lecture that, say, lasts over an hour? Are you getting bored? Is your mind wandering? Well, there was a study from Bly that looked at the normal attention during lecture and attempted to use heart rate as a measure. So this was a standard uninterrupted lecture where the professor spoke, similar to the idea of a video here, where just for over an hour, and they measured heart rate over time. Well, how does that work? Over time, it starts out at averaging 85 beats per minute, and by the end you're down into the high 70s. Does that tell us that over time you're less attentive? Well, is heart rate a good measure of attention? What else influences heart rate? Tell me. What kind of things influence your heart rate? Do some people have higher or lower heart rates? What about caffeine, other chemicals, level of interest? That's the goal here, to say that the more interested you are, the higher your heart goes up. And this is studies done with infants rely very heavily on this. But other things do measure, influence heart rate, and we have various things. And for instance, if you rush to class, your heart rate's going to be higher, right? You've just been working, you've just been moving. If you were sitting in that class that another class was in there previously, do you think you'd have the same increase in heart rate than if you just ran across campus? Well, how do we measure attention? Because we're thinking about how you and your body regulates your ability to function. And over the course of this discussion, we will actually see some areas where we can do better. We can actually, in some ways, hack our physiology in order to improve our ability to function. We know, for instance, that caffeine levels can influence our heart rate, right? And they can influence, are they influencing our attention? Perhaps to a certain amount. But we also know about the diminishing returns. Does your body adjust? What happens over time when you have, caffeine every day? How does it function? And what gets your attention? In a live lecture, we like to have questions. We like to have engagement. We like to do different things so we can see what's actually, working and have people kind of tune in rather than kind of sit there scrolling on their phone or whatever it is. Well, the idea here is a link between the function of the mind and a physiological measure. This is your heart rate. So can we do this? Well, in PhysioPsych labs, we try to do this. And there are a number of ways that we attempt to measure the link between your mind and your behavior. And when we talk about regulation, we're talking about, your changes to your body states. How does your body affect the mind? And how do we maintain normal functioning? What's happening in the brain that allows us to do so? And really, our brain spends a lot of energy on exactly this. So, we're going to now understand what homeostasis is. It is basically your biological processes that your body keeps within a fixed range. We tend to think of temperature regulation because that's the biggest thing your body does. Your body spends the most time regulating your body temperature, and your body temperature is kept within a pretty tight range. In fact, too high or too low can be deadly. And mammals all tend to have a pretty tight range, even birds, right? Also, a pretty tight range in terms of what your typical body temperature is. Well, what this also means is that we are regulating what we call these set points. So you've got homeostasis, which is maintaining these biological processes within the set range, and we've got allostasis, which is the adaptive way in which your body changes its set points in response to changes in life or the environment. Consider, it gets colder in the winter for most people, and when it gets colder, when it first drops, you're often very cold. And then after a month or so, you've adapted somewhat. Whether that would have required a jacket and you'd be shivering, maybe you're not doing so much. In some ways, your body has adapted. In the summer, maybe it gets hot, and it's the same thing. Your body adapts to maintain your set points in some way. And we look at these other options. Levels of water, oxygen, glucose, calcium, proteins and fats and acidity. All of these things have to be kept within fairly tight windows. And a lot of medical tests are going to see, like, are your expected levels of these things in those windows? And if not, that's a problem. Over the course of this process, we use positive and negative feedback. So positive feedback increases changes, and negative feedback reverses those deviations from what we call those set points, depending on what we need to do. So as we're eating, your body is undergoing rapid change in order to increase levels of certain hormones and then do digestion. When your body temperature changes, what happens? You have to cool that off. When you have a fever, you might increase that for some potential positive benefit. If we were to look again, if we say, okay, now we pause, we count to 10, and we measure our heart rate. What is your heart rate now? Has it changed, or is it the same? What's your attention level? And once again, can we do a better job of understanding regulation and understanding this link between attention and the body? Okay, so here's those definitions again. Homeostasis maintains your set points. Your body is constantly working to maintain your basal metabolism, your temperature. Allostasis is altering the set points to adapt to the environment. Think about big changes that you might have to make. For instance, how many red blood cells do you have? Might not be something you think of that often, but what if you were to go spend some time at a high altitude, right? Say you were going to Mexico City or Cuzco, Peru, where now you're 10,000 feet in the Andes, right? The air is relatively thin, and when you first start breathing the air, you have trouble catching your breath. After a few days, your body has produced more red blood cells in order to carry more oxygen and make use of the lower air availability. And after a week or two, no problem. We see athletes who will use this in order to improve their performance by working out somewhere at a higher altitude in order to force their body to produce more red blood cells. So your body has adapted how many blood cells it has in order to deal with the environment. Well, the biggest thing your body does is temperature regulation. In fact, about 2/3 of the energy you use every day is spent on regulating your body's temperature. That's wild. You consider, we know our brain uses a massive amount of our body's energy, and most of the rest of it is going to this, to maintaining your temperature. And so you need to keep this constant rate. And we do this through various things. You see the shivering duck here, who is heating up through shivering. This also tells us something interesting, which is, you ever jump from like a hot tub into like a cold pool or something like that, or vice versa? Your body's working very hard to change, to adapt to that temperature. This shock can cause incredible stress in the body, and yet in other ways it can, you think about, burn off a lot of energy. When you exercise, your body heats up, uses a lot of energy to cool it back down. So we have these processes about how we're kind of burning calories. Now there's two different ways that species can deal with body temperature. The first is called poikilothermic. These creatures are traditionally called cold-blooded, but that doesn't really, it doesn't mean what you think it means. It basically is better to describe a snake as environment dependent for temperature. And in the same way, if you had damage to your body's ability to regulate temperature, you would have to behave in the same way, which is to use the environment to heat up or cool off. So amphibians, reptiles, fish, their body temperature matches that of the environment. They don't have the internal physiological mechanisms to regulate temperature, and so that's why you'll see a snake on perhaps a cool day basking in the hot sun. And when it's cold, you don't see them at all. They're effectively hibernating. They're effectively staying underground in order to maintain as warm as they can. And then when it's summer again, when the air heats up and they're able to better maintain their temperature, now they're back and more active. But what we also know is this: if you've ever had a pet reptile, they don't eat nearly as much as a pet mammal. And if we think about it, if we're spending 2/3 of our energy regulating variable metabolism, they don't have to. So they have a far lower caloric need because they're not performing the same tasks that we are. We, like the adorable puppies here, are homeothermic. And this means that we use the internal physiological mechanisms to maintain an almost constant body temperature. Us, mammals like us, birds, it requires energy. It requires more calories. And how do we maintain it? Well, if we get hot, we sweat, animals pant, and then if you get cold, you shiver. As humans, if we get hot, we turn on the AC, and if we get cold, we turn on the heat or put on a sweater. Now, we have a body temperature about 98 degrees Fahrenheit, which varies within humans. There's a couple degrees variability there. But what's interesting is almost all mammals and even most birds maintain a range that's within a few degrees of this. And this is because of a couple of things. One, we want to keep our muscles warm so that we can be active under any circumstances. In the winter, you're ready to go for a run because your muscles are warm. You're maintaining that temperature. A snake that's in the ground cannot. Absolutely not. Its muscles aren't warm. They're not able to do the things they would do under heat. And if you've ever seen a reptile in cool weather, they move slow when they're cold. They just aren't able to function in the same way. You get too high, though, and proteins in the body break down. And that's bad. So you want to keep in this basic range. And once you hit, that's why when you get a fever that's too high, it's really bad. And we'll kind of look at some of those numbers there. But when you get too cold, you can have more kind of invasive growths, freezing and cell damage. Your reproductive cells need to be relatively cool. You may have noticed that males tend to keep their reproductive cells on the outsides of their bodies because it's easier to regulate the heat that way, which actually means it's more difficult for women with internal, sex organs to maintain that temperature. All right, how are we doing? This is the adaptive way the body changes its set points to deal with large environmental changes. What is this called? Is it homeostasis, allostasis, poikilothermic, or homeothermic? And the answer is allostasis. Big environmental changes. This is the example of going to a low oxygen environment, for instance. This is when the organism's body temperature matches that of the environment. Homeostasis, allostasis, poikilothermic, or homeothermic. And it is poikilothermic. We also see examples of people's set points changing and their bodies adapting. If you live, for instance, these classes that we're doing are generally in Southern California. If you see people in January wearing tank tops and shorts and flip-flops, you probably immediately start to think this person is probably from a cold climate, right? Because their body's adapted to that. And now in this freezing 58-degree weather, they're like, this is warm. Now we look at asking questions like this because it actually helps us in our learning process. Looking at how attention changes. One of the things that another study that was done showed that when you stop and you actually have to do something during lecture, it resets in a way your ability to attend. Using that kind of information can help us through learning. We also know, as mentioned very early on, that if you answer questions like this, you do better. In class, we're holding up an index card. Now, when we look at our internal experiences, pain is interesting. Sometimes we feel pain related to where our internal organs are. Sometimes we don't. So you look at the classic left arm pain for a heart attack, right? You see that is where the heart is felt, from the left area around to the side of the heart, because the heart's more central, all the way down the left arm to the left pinky. But what's interesting about this too, is worth noting, is that women have a different referred pain experience, which means we have to be cautious in talking about things like this. If you have, for instance, if heart attack symptoms, they might not appear the classic, left arm pain. There's a number of other things, such as anxiety or nausea. So it's good to kind of know what those are. When you look at these, you can also see that, for instance, kidney pain can go to the back, to the legs, isn't necessarily felt where that is. We look at what the hypothalamus does in regards to what we care about here, and it's regulating hormones, producing and directing the production of hormones in order to regulate physiological activity. You see, for instance, the examples here. You've got the neuroendocrine system and the autonomic nervous system, where you've got these various hormones producing to do different things. For instance, sympathetic and parasympathetic and even enteric behaviors. And we'll look at a little bit about what these hormones are and how they work. Here is something you've seen, which is the brain and pituitary and hypothalamus. So where in the brain is the hypothalamus? Fairly small, below the thalamus, under the thalamus, containing a number of nuclei. And we're going to be looking at a number of these nuclei to see kind of what they do and how they function. And we're aware also that the posterior pituitary, which is connected directly to the hypothalamus, is effectively also the same type of cell, so producing hormones that are able to be dropped directly into the blood. When we look at thermoregulation, for instance, hypothalamus, we see this is primarily in the preoptic area, which is called the POA/AH, preoptic/anterior parts of the hypothalamus. And we see that in this area here, this kind of green area, and this purple here. So we see how these things are related to thermal regulation. Now, you can actually heat or cool this area and cause a physiological response. So animal studies will put an electrode directly into these areas, heat them or cool them, and you can actually see the animal either start sweating or freezing, which means this nucleus is monitoring its own temperature to know what it should do. But it also receives input from temperature-sensitive receptors in the skin. And we see Also, this red one here is the mammillary body, which is often considered to be a separate thing, right? You can actually see it on the ventral surface of the brain, where you can't really see the hypothalamus. But what's interesting about it is it's involved in feeding behaviors, which is, again, part of the regulatory stuff. And I think the reason we think of it as separate, its own thing, is it's visually separate, while these things are kind of a bit more jumbled. And again, things aren't quite this clear, but this is the general idea. And the one that we've spoken about before is the suprachiasmatic nucleus, which we discussed in dreams and consciousness, because this is involved in regulating our circadian rhythms. So again, it's all regulation. It's all monitoring and maintaining our set points through homeostasis. Well, fever is part of a process where you get these leukocytes released by immune cells, which release cytokines. And these cytokines are responsible for attacking the bacteria and viruses, but also stimulate the vagus nerve. And this causes the body temperature to rise. So there's clearly this, logical process of creating a fever. But this also means that the fever has certain things that it has to do. So the vagus nerve stimulates the hypothalamus, initiates a fever, and it can slow the growth of some bacteria. And the belief is that by heating the body, you both boost the immune system's process, right? You heat up and you go faster, just like you cool off and you slow down with our poikilothermic organisms. So you heat up the body a little bit, you get this immune system boost. And you also, in some cases, may slow the growth of certain bacteria. The benefits, however, max out at about 102, 103 degrees. When you hit 103 degrees, you stop getting those benefits. And now the body has to work really hard to cool off. So you're using, now the benefits diminish. And by the time you hit so basically, if you have a fever of 101, 102, you don't really need to do anything about that. That's your body fighting the infection. But when you hit over 103, that's when you want to kind of start monitoring and taking care of that fever, because it's not helping you as much. Once you hit, if I were to hit 105, I would be on my way to the emergency room, because once you hit 109, it's life-threatening. And remember, at certain temperatures, proteins start to break down. Well, your brain is full of proteins, so you're basically doing serious damage. Which part of the hypothalamus is the control center for body rhythms? Is it the supraoptic nucleus, the suprachiasmatic nucleus, the preoptic area, or the ventromedial nucleus? And it is the suprachiasmatic nucleus. About what percent of your body's calories are burned in order to maintain thermoregulation? 25, 33, 67, or 75? And the answer is about 67, which is about 2/3. Now, we're also working very hard to regulate water. Water constitutes 70% of the mammalian body, and it must be regulated within narrow limits. The concentration of chemicals in water determine the rate of all chemical reactions in the body. So you've probably heard of those cases where there's this urban legend, which has some truth to it, about a radio station having a water drinking contest and somebody died from drinking too much water. Well, when you drink, your liquids, you're motivated to drink. You've got these processes that motivate you to drink in order to maintain the right balance. And sometimes you crave different things. Well, you've got certain ions in your blood that help to regulate processes. What are the ions, for instance, that our brain relies on in order to create action potentials? You probably recall that this is a balance of sodium and potassium. Well, these things are soluble, and the more water you drink, the more that's kind of pulled out, right? It dilutes these. So somebody who drinks gallons and gallons of water in a short period of time is excreting these necessary ions, without which your neurons can't fire, your heart can't beat, you can't function. So we're actually monitoring these things to know what we need. Well, our bodies also do a good job of conserving water. So if you are, not drinking a lot, you can really concentrate the urine and pull some of that liquid back into the body. You can decrease sweat and other autonomic responses, but over time this can create heating, and this can cause, heat stroke or even death. Maintaining your body's liquid levels is extremely important. The most common thing people do to regulate their water amounts are drinking more water than we need and excreting the rest. If we live in a place that has easy access to clean water, many people even carry a refillable water bottle with them and simply are able to easily maintain this level throughout the day. Well, as our water levels change, our blood volume changes, and this can be problematic. If we didn't have a way to regulate basically the diameter of our blood vessels, if you were to become dehydrated, your blood would simply not be able to flow to your brain and you would pass out. If you drank too much water, your blood pressure would become so high you could, cause the blood vessels to burst. So what you have is vasopressin, which is a hormone released by the posterior pituitary, and it constricts your blood vessels, right? So it's able to kind of shrink the diameter. So if you become dehydrated, you are able to, very quickly constrict your blood vessels, and your blood is still able to flow and reach all the places it needs to. You're also considering this, that as your blood volume increases, you will produce less and allow these things to dilate in order to keep this from happening. As something happens as we age, is we become less responsive here. We're not producing as much hormones, and it can cause greater swings in blood pressure. This is part of the hypothalamus and is a primary control center for thermoregulation. Do you remember this? It's been, my goodness, so long. Is it the supraoptic, suprachiasmatic, preoptic area, or ventral medial? And the answer is preoptic. Preoptic and anterior. Okay. How does this work in terms of fluid? So I mentioned what happens if people drink too much water, right? You end up losing these ions. Let me explain how that happens. So what's interesting is eels and salmon exist both in freshwater and saltwater. And you're probably aware that if you take a freshwater fish, put it in saltwater, it dies very quickly, and vice versa. But you've got these species that are able to migrate back and forth, and they have similar osmotic pressure to we do, which is, basically your components of how the solute to liquid concentration in your body. So how do they do this? Well, in freshwater, ions are actively absorbed through the gills. If you go up into the mountains, the water has a very low ionic content. It's very much snow melt in some cases and runoff. And there are certain places up in, for instance, the Sierras, where the ion concentrations are so low that animals have a serious sodium deficiency and have to work very hard in order to get whatever salt they can. So for fish in this case, they drink as much water as they can, discharge the liquid, and absorb all the ions. And when they make it to seawater, they drink a lot of water, keeping the liquid and expelling the ions. So their gills and kidneys are doing a good job of, pulling in what they need and excreting the rest. Well, here's how osmotic pressure works. Basically, you ever take a little food coloring and drop it into water and you see it diffuse, right? Or you mix a couple of liquids together and you see them very slowly kind of mix. A little cream in your coffee, right? And it kind of starts to spread out. This is diffusion under normal circumstances. Things want to diffuse in liquid and spread out as much as they can. Well, when you use a semi-permeable membrane and you allow only certain things to pass it, as in the example here, you can see that you put glucose in one side, it's all water, and you only put glucose in one side. The water can pass through, the water molecules can, but the glucose cannot. What you see is the water rising. So even though you've got pressure, you've got like gravity that wants these two water levels to be the same, because you've got these ions over here, well, these solutes over here, I should say, you're actually pulling water in over there in order to kind of create this more of a balance? Well, our bodies are actually monitoring the amount of ions and are aware of this. And so you've actually got two different kinds of thirst. Sometimes you're thirsty for just plain water. Sometimes you're thirsty for something like a salty water or a soda or something that has some ions in it. Well, the reason is if you eat a lot of salty foods, your body is craving this pure water. This is called osmotic thirst. If you are losing a lot of fluids through sweat, exercise, or bleeding, you have hypovolemic thirst, low volume, and your body wants not just water, but salty water. And so you will actually crave various things. Your osmotic thirst, basically, you need to maintain a concentration of solutes at your fixed level, and the solute level has risen. And so by increasing your liquid concentration, you're able to bring that back to normal. Eating salty foods causes sodium ions to spread through the blood and the extracellular fluid. And here's another example of the semi-permeable membrane. So here you have the same kind of thing, right? But now we see that we have a little more, still more glucose on one side than the other, and it's pulling the water more to that side to maintain these levels. So even though you've got gravity pushing down that wants these things to be even, you have it actually osmosis pulling it up. So the brain detects this pressure from receptors around the third ventricle. So the ventricles, we recall, are filled with cerebrospinal fluid, and the cells around it are actually producing cerebrospinal fluid. And the pressure of the fluid is related to the water pressure in the body. The OVLT, we'll look at that, and the stomach receptors also detect salt. So you've got these different functions. So here's the OVLT, the organum vasculosum laminae terminalis. It's and we also have the subfornical organ, and they detect osmotic pressure and salt content. And we see this is about where we are. The receptors in the OVLT and elsewhere tell us about these pressures and salt contact. And we've got our supraoptic and paraventricular nuclei, which both control the rate at which the posterior pituitary releases vasopressin. Because what we want to do is connect the information from the OVLT to other areas that can actually control this pressure. We also have the lateral preoptic area that we see here, which tells us about should we drink. And here's some kind of zoomed in at these. The preoptic area and the lateral preoptic area controlling drinking. The supraoptic and paraventricular nuclei, supraoptic and paraventricular nuclei control the release of vasopressin from the posterior pituitary. And they can do that because there's a direct connection here where the anterior pituitary has to get its signal from the posterior pituitary by the posterior pituitary releasing hormones into the blood that then make it back and are detected by the anterior pituitary. This is part of the hypothalamus and is the primary control center for thermal regulation. Now you've got this one, right? Is this the supraoptic, suprachiasmatic, preoptic, or ventromedial? And the answer is, this is the preoptic. And then we have the part of the hypothalamus that controls the rate at which the posterior pituitary releases vasopressin. Is this the supraoptic, suprachiasmatic, preoptic, or ventromedial? And this is the supraoptic. And the other one that does this too is the paraventricular, that control the release of vasopressin. What causes osmotic thirst? Is it bleeding, eating salty foods, sweating, or having a low salt diet? And the answer is blue, eating salty foods. You increase that pressure, and so you bring in water. Now, osmotic thirst is going to create this craving for water, which then has to be absorbed through the digestive system, which means we have to have another signal here to tell us, because you start drinking And it takes about 15 minutes before your body can absorb this liquid and start to make use of it, which means you've got to stop the drinking. So you've also got information in your stomach. And this is telling us about the water content of the stomach and intestines. If we were to drink water nonstop, what would happen? Well, we could go the other way. We would now be out of balance. You could actually rupture some of these organs too much. Then we consider hypovolemic thirst and sodium-specific hunger. Hypovolemic thirst is thirst associated with low volume of body fluids. It's triggered by the release of the hormones vasopressin and angiotensin II, which constrict blood vessels to compensate for a drop in blood pressure. So we've seen this, right? Hypovolemic thirst has low blood volume of body fluids, which means we need some, but it's not just water we want, but it's also the solutes within it. So osmotic thirst is triggered by too much salt. Hypovolemic thirst is triggered by liquid loss. So if you wanted slightly salty water, if you wanted something like a soda, what kind of thirst is that? Osmotic or hypovolemic? It's hypovolemic. We also have something called sodium-specific hunger, which is a strong craving for salty foods. So you want something that is salty, and this is a certain type of hunger, which is related to low solute in your body. Now, animals vary in eating strategies, but humans, especially modern humans, are able to eat more than we need. We tend to have access to a lot of food. Whether or not this is healthy food is a separate issue. And we've already seen examples in this course on what is the benefit of eating healthy foods, certain foods specifically having mood improvement benefits, like very, very clear and measurable mood improvement benefits. And a lot of people eat very poorly. Now, we've got a number of factors involved, and one of these things is the vagus nerve tells us about the stretching of the stomach. However, the splanchnic nerves tell us about the nutrient content of the stomach. So think about what this means. You ever eat a lot of food and then you're hungry like half an hour later or an hour later? Well, what kind of food was it, right? Perhaps you ate something that was, kind of like what they call empty calories, something that digests very quickly and that fills your stomach, and then there's not enough nutrients in it. So your body knows, hey, eat something else, jerk, give me something with nutrients in it. Which is why, for instance, things like high fiber foods, which stay in the stomach longer, are extremely beneficial, right? High fiber, high nutrient foods, leafy greens and vegetables, for instance, tend to take longer to digest and also have much higher nutrient components, which means your body is going to, not be as hungry, which means your body is actually aware of what you need. And if you give your body your physiological needs, you can control, for instance, things like binging, because you're not going to have that same desire. Now, I understand also that there are certain, psychological conditions that go beyond the simple, oh, I'm hungry, I'm just going to eat. But for most people, adapting the diet can have extreme benefits, not just in weight, but also in mood and health. Certain things they're always looking for quick fixes, right? So people will go onto these short-term diets that will have rebound effects. You've heard of yo-yo dieting. So as we look at how this works, we understand that, yeah, dieting can help people lose weight, but your body adapts to it and has immediate effects on your metabolism that are not necessarily beneficial, which means you're going to gain back once you return to what your typical diet is. Another thing is, for instance, gastric bypass surgery, where they'll actually cut off part of your stomach or shrink your stomach in some way. In this case, they attach a chip to the vagus nerve to send signals to the brain to reduce appetite. The problem is we adapt to these things. So these things tend to be temporary. And we'll look at kind of how this works. Well, the duodenum is right below the stomach. It's part of the small intestine where you start to absorb a lot of nutrients. And so you can kind of see right when you leave the stomach, you enter the duodenum, the small intestine. And this being filled can also make us feel not hungry. And it releases the hormone CCK. This can help to regulate hunger. CCK does this by closing the sphincter muscle between the stomach and the duodenum, causing the stomach to hold its contents and fill faster. So again, stuff when you start to need to extract the nutrients, you slow down digestion. And this makes us feel full faster and less hungry. Stimulating the vagus nerve sends a message to the hypothalamus to release another chemical similar. Now, how does this work and relate to our actual eating habits? Well, when we eat refined sugars, this leads to a high release of insulin. So, sugary snacks, sweets, chips, these tend to be refined, which means they're simple carbs. So what happens is the glucose is very easily digested and dumps in the blood's stream quickly. Well, what this does is it creates an insulin spike, which means, there's a lot of glucose in your blood. Crank up the insulin, and insulin, we'll see, is part of the process that allows glucose to be pulled from the blood to be stored in fat cells. So not only does glucose increase the size of your fat cells, it also, when you have a lot of it all at once, gets pulled from the blood so quickly that now you go the other way and you crash. You end up having less glucose than typical. So how do we hack this in order to improve our attention, our concentration, and our function? Well, complex carbohydrates, such as certain nuts, popcorn, surprisingly, right? Of course, the way I eat it with all the butter in the world and salt, probably not the best way to do it, but it's a complex carb, which means it's going to be digested more slowly. The glucose is going to be, released into your blood more slowly. The insulin levels aren't going to spike as high, which means you'll get this kind of steady stream of glucose. What happens, you have a big meal, you digest it, and then your body releases this glucose into the bloodstream. After a certain amount of time, there's no more. And so what your body does is you're hungry again. It boosts this insulin. Hypovolemic thirst causes a craving for what? Salty water, pure water, salty food, or low salt food? And the answer is salty water. Now, sugary snack and complex carb, what's the difference? Is it the complex carb causes an insulin spike? Is it the simple sugar causes an insulin spike? Or is it the complex carb is pulled out of the blood faster? And the answer is the simple sugar causes the insulin spike. We just saw the complex carb slows down digestion. You don't feel full you feel full longer. You're not feeling full as hungry as quickly. And your body makes better use of the nutrients, and you don't end up stuffing glucose into your fat cells because a nice regular amount is released into the blood that can be used. Now, glucose, insulin, and glucagon influence feelings of hunger. So, most digested food enters the bloodstream as glucose. We need this. This is what our body and brain uses for energy. And when levels are high, the liver converts some into this glycogen, and fat cells convert it into effectively fat. When low, the liver converts it back into glucose. And this is how you see the weight gain. It's the high intake which leads to that. Insulin allows glucose to enter the cell. And these levels rise not just when you've eaten or are eating, but also when you're getting ready to eat. It kind of starts pulling the rest out. High levels of insulin, however, generally decrease appetite. Now, Glucagon is released by the pancreas when glucose levels fall. It stimulates the liver to convert some of its stored supplies into the glucose in the blood. And if insulin stays constantly high, the body continues rapidly moving the blood glucose into the cells long after a meal. In people with diabetes, for instance, insulin levels remain constantly low. The blood glucose levels are high. This means people with diabetes sometimes will not seek treatment or regulate because they're not hungry. They feel like they have energy. This glucose is not being pulled out. But the high levels of glucose in the blood, the danger of this is serious damage. Basically, especially in the periphery, things like your eyes, certain organs are extremely sensitive to these high levels of glucose in the blood. And that's why people with severe diabetes that are untreated will see, the loss of extremities and vision damage. Hunger regulation is accomplished monitoring fat in the body. This is interesting too. The body's fat cells produce leptin, which signals the brain to increase or decrease eating. Low levels of leptin increase hunger. High levels increase physical and immune system activity. However, high levels of leptin don't necessarily decrease hunger because when people become obese, they become insensitive to leptin. So if you are have a lot of fat cells, you've got, you're producing leptin, but your brain's not doing a good job of dealing with it. In fact, it causes damage. Obesity causes damage to the endoplasmic reticulum of neurons in the hypothalamus that are related to the regulation of feeding. And this means that you're going to have difficulty. What's interesting and to most people upsetting is the cure is diet and exercise. It has been shown that physical exercise produces chemicals in the immune system to repair the endoplasmic reticulum in these hypothalamic neurons necessary for regulating this. It's all part of a, general health. We also have our arcuate nucleus, which is part of the hypothalamus and contains two sets of neurons that signal hunger and are sensitive to satiety. So basically allowing us to understand. The paraventricular nucleus releases melanocortin, which limits food intake, and deficiencies of this lead to overeating. Now, our last consideration in this area is to look at something called the enteric nervous system. This was mentioned as part of the autonomic nervous system. But for a very long time, the autonomic nervous system was really considered to be two things, which was the sympathetic and the parasympathetic nervous system. The sympathetic being that fight or flight, ramp you up. The parasympathetic being the rest and digest. Slow you back down, bring you back to typical. It's interesting, however, is this. The enteric nervous system has 500 million neurons. This is a lot more than the spinal cord. Parts of the enteric nervous system, parts of the autonomic nervous system is the enteric nervous system, considering also the sympathetic and parasympathetic nervous systems. These are separate, but the enteric nervous system is influenced by them. So for a long time, it wasn't really considered to be a separate thing, but there's some very specific types of neurons and structures in the enteric nervous system. And here's how kind of new it is. The Journal for the American Neurogastroenterology Society only included neuro since 1994, seeing the gut-brain link. And it's often referred to as the second brain, right? Your stomach, your gut. It tracks nutrients and responds on its own. It communicates with your brain, but it functions separately, and it can function separately. You cut the vagus nerve, damage the vagus nerve, no problem. It can still function on its own. It uses over 30 neurotransmitters, and interestingly, we think about what's serotonin for, what's dopamine for. Well, the majority of your body's serotonin, the vast majority, is being used by the enteric nervous system in your gut. And half of the body's dopamine is also being used here. It has a functional blood-brain type barrier, blood protecting the neurons. And it has glial support cells that are similar to the astrocytes in the brain. So it's a very interesting area of research, very clearly its own thing, and I think we're going to see a lot about it in the future. For instance, there's some recent theories that suggest things like Parkinson's disease may have a gut link where they follow, it starts in the gut and kind of follows up into the brain. So some very interesting areas of research here. I hope you've enjoyed our discussion of the hypothalamus and process of homeostasis, and I look forward to future discussions with you. Thank you.